This is my Physics 2211 Lab 3 report about the black hole. In this lab, the purpose was to apply the momentum principle and the universal gravitation law to determine the mass of a black hole with a star orbiting it. Then we used the mass to determine the initial velocity of a spaceship flying from a planet orbiting the black hole to leave the system without crashing into either the planet or the black hole. An overview of the results is that the mass of the black hole was found to be 1.622 times 10 to the 34 grams, and the initial velocity of the spaceship to escape was negative 2.25 times 10 to the 7th in the x direction and 6.3 times 10 to the 6 meters per second in the y direction. The fundamentals in this lab include Newton's second law of motion, which gives that the net force is equivalent to the change in momentum over change in time or mass times acceleration. We also know that the net force is equal to the perpendicular net force plus the parallel net force. And also from Newton's second law of motion, we can get the velocity update and the position update formula. Also, since gravity was the only force in the system, which is not a constant force, we can assume that V average is approximately V final. The next fundamental is the universal gravitation law, which is given by this equation here, where g is the universal gravitation constant. In part 1, determining the mass of the black hole, the system was the star orbiting it, and the surroundings was the black hole, since we were tracking the motion of the star to figure out the mass of the black hole. The initial conditions were that the mass of the star was 2 times 10 to the 30th grams, and delta t was 86,400 seconds, which is 1 Earth day, and we started at time 0. This is the code for part 1 of the experiment of determining the mass of the black hole. Over here we had our constants such as the gravitational constant, the mass of the star, and the delta t, and using that we used the initial velocity and mass of the star to find the momentums at the initial and final point, and then we found the change in velocity and change in momentum. We could then calculate the change in momentum per change in time, which is equal to the net force as given by Newton's second law. And then we can find the parallel component of force by taking the change in the magnitude of momentum per time and multiplying it by p hat, which is the direction of the momentum. Using that, we could then use the fact that the net force was equal to the parallel plus the perpendicular force to find the perpendicular force. And then, since the perpendicular force is the one that was caused by gravity, we can plug it into the universal gravity equation and isolate the mass of the black hole to find it. These are the results from part 1 of the experiment, where the average mass of the black hole was found to be 1.1622 times 10 to the 34th grams. We also found that the net force was 8.862 times 10 to the 28 newtons, the parallel net force was 2.37 times 10 to the 28th newtons, and the perpendicular force was 8.55 times 10 to the 28 newtons. For part 2 of this experiment, we are finding the velocity needed for the spaceship to escape the system without hitting the black hole or the planet. The system included the spaceship and its surroundings were the black hole and the planets. The initial conditions were that the mass of the black hole, as found before, was 1.1622 times 10 to the 34th grams. The mass of the planet was 9 times 10 to the 28th grams, and the mass of the spaceship was 7 times 10 to the 10th grams. This is the code from the second part of the experiment. Here we inputted the mass of the black hole as found before, as well as inputting the other initial conditions and the time frame that we ran the simulation. Right here we have the velocity of the spaceship, which is what we are looking for, and we used a guess and check method to figure out what the right initial velocity was. With those, it then went into a calculation loop where we had a constant calculation of the distance from the black hole and ship to the planet and from the black hole and planet to the ship. And with those, we could use the universal gravitation law to find the force acting on all the bodies at the same time and calculate the net force on the planet and on the ship. With that, we could use Newton's second law to get the velocity and position update formulas to track the position and velocity of the planet and ship over time. And using that, we could put in different initial velocities for the spaceship to figure out what the right initial velocity was for it to escape. The results of this part of the lab showed that the initial velocity of the spaceship to escape the system without colliding was negative 2.25 times 10 to the 7th meters per second in the x direction and 6.3 times 10 to the 6th meters per second in the y direction, and it escaped along this path right here. We found that as the ship gets closer to the black hole, the force kept changing, which changed the direction of the momentum, as seen by its curving motion right here, but the ship was able to escape the system and did not crash into the planet or the black hole at this initial velocity. The errors in this lab include that trial and error was used to find the initial velocity in part 2, and there may be various other velocities that get the ship closer to the black hole without crashing into it or the planet while still escaping the system. Additionally, the mass of the black hole was just an average of all the calculations, and letting the code run for a longer time would get more measurements and would lead to the calculated mass being more true and more accurate to what it actually is. So for our what does it mean question, the first one is how are the net force and its parallel and perpendicular components different from the rate change of momentum and its parallel and perpendicular components? Because of Newton's second law, we know that the net force is equal to the rate of change of momentum, and therefore the parallel and perpendicular components are going to be the same for each. However, the rate of change of momentum is much easier to calculate in this case, since we only need to know the change in velocity, the mass of the system, and the time interval, while for force you would need to know each individual force acting on the system, which can be very difficult in large scales. And for the what if question, we asked what would the initial velocity have to be in order to enter some kind of orbit around the black hole? Many different initial velocities could work for this, but the x velocity had to be lowered so that it didn't fly away like it did in the initial calculations. The initial velocity that I found to create an orbit was negative 3.2 times 10 to the 5th meters per second in the x direction and 9.5 times 10 to the 6th meters per second in the y direction. And it created an orbit along this pink path right here.